Welcome back. So in the last lecture we have discussed about our battery management system, its roles and activities, and we have understood that whenever we connect the charger to electric vehicle, BMS will be the one which will be deciding the rate of charging and the type of charging. And we have seen what is the meaning of cell and how an battery pack is manufactured based on the voltage and the capacity requirement. So based on the voltage requirement, we will be connecting n number of cells in the series, and based on the capacity requirement we will be deciding how many cells will be there in the parallel, and in turn we will be developing the battery pack. So and we have also understood what is the importance of our cell balancing, why it is required, so that uniform charging and discharging will be obtained among the all cells present inside the battery bank. Then continuing from that point, there we have seen that BMS will be communicating various things with the charger, and there will be a requirement of communication between the battery and the charger, or the BMS and the charger. So here when we connect the battery charger, so it will be having this many tasks which has to be handled by the BMS. So there will be a communication between the charger and the vehicle. So there are many types of communication protocols which will be used for this type of communication between the vehicle and the charger. First is your CAN bus, which is the most common one. The other one is SPI bus and I2C bus. So these are the different charging protocols which are used for communication between the BMS system and the onboard of the vehicle and the charger. So this is the typical layout of your CAN bus communication system. So we will be having the CAN bus lines which will be connected between the vehicle and your charger, and it will be connected inside the battery pack, and the BMS system will be developed. So here we will be having the communication through this any one of the protocol whichever is used by the manufacturer while developing the electric vehicle and the charger systems. So most common one will be our CAN bus communication, which is widely used in the electric vehicles. Then with this we will stop our discussion on the battery packs. Now we will move on to the last component which is left from our electric drives point of view. So that is our vehicle motor. So which will be present on board, and it will be an electric motor, and most of the cases for SUVs and for heavy electric vehicles it will be a 3-phase machine. So let us see what will be the type of machine which will be used and what is the requirement for the motor to be qualified to be an EV motor. So first requirement for any machine to be qualified as an EV motor, first is it should have high torque density and high power density. Why these are important? Why high torque density is required? So for a given power rating, or the for a given speed of the vehicle, maximum speed of the vehicle, so if we have higher torque, so the size of your motor will be reducing. The same thing is true with the power density. So if your power density is higher, so the size of the motor or the weight of the motor will be less. So our efficiency of the electric vehicle will be higher, or it can cover longer distance with the same battery pack. Ability to generate proportion torque over a wide speed range. Okay, so our vehicle will be moving over a wide speed range, that is it should start from 0 and it should go to the maximum speed, and the motor should have an better torque performance for the wide speed range. Okay, so this is one of the reason why we do not use DC machines. So those we will see in the next slide. So wide speed operation, low speed creeping speed, so it means it will be moving at a very dead speed or nearly 0 speed. High speed cruising, so it will be at the top speed, and the motor should have the facility of providing these two range of operations, so that the vehicle can move without any difficulty. Higher efficiency over a broad torque and speed range. So the efficiency of the motor, first is it should provide the better torque performance over a wide speed range. And the additional requirement is its efficiency should be better over the entire range. Wide constant power region. So we will see this while going into the different types of control methods used. So what is the meaning of this one? Then higher starting torque. So this will be required for vehicle launch. So it comes from the rocket launching. So the word launch, it means the vehicle will be reaching a higher speed within a less number of time. So why this high torque is required? So first is our, when we go for sports vehicle or high performance vehicle, there we want the speed to increase rapidly. So during that type of application we will be requiring higher torque. When there is sudden acceleration or we are climbing in an hilly terrain, so we will be requiring higher amount of torque. High intermediate overloading capacity. Suppose there is a traffic signal and it has become green, suddenly the user presses the acceleration pedal. So we may have a tendency of going into the overloading condition. So our motor should be suitable to handle overloading to a certain extent. High reliability and robustness, because compared to the other motors which are used in our industrial drives, so there the motor will be stationary. We rarely move the motor with the test bed, the bed where the motor will be fixed. Whereas in this case, this motor will be moving with the electric vehicle, so it should be more robust and reliable under such harsh working condition. That is, it has to move with the vehicle and it will be subjected to various oscillations and vibration during the vehicle movement. Low acoustic noise and vibrations. So although the vehicle will be going through the potholes or speed breakers, during that time also it should not produce any type of vibration. Low acoustic noise inside the vehicle, we should not hear the noise of the motor. So these are the requirement of our electric, any electric motor to be qualified as an electric vehicle motor. Compact size and reduced weight. So this is again with the same torque density and power density terms. So it should be as small as possible and it should have as small weight as possible, such that the vehicle will not be loaded because of this payloading of the motor. Good thermal performance and cooling capability, because the vehicle will be moving, so it should be able to withstand. If the vehicle is moving for a longer time, then also it should have the temperature within the prescribed limit. Then let us see, we have seen now just what are the characteristics requirement from the electric motor inside the electric vehicle. Now let us see what are the types of motors available with us and which one will be suitable for our electric vehicle application. So broadly we can classify the electric motors in two ways. First is our commutator based and your commutator less electric motors. Okay. So commutator based motors, the best example is our DC machines, where we will be having self excited or separately excited. It will be requiring another DC source to excite the machine. Whereas self excited, the same supply which will be given to the motor will be used for field excitation as well. So in this case we have series and shunt, and self excited we have field excited or permanent magnet excited. Okay, so these all are based on our DC machine architecture. So DC machines, as I said in the last slide, we require wide speed range of variations. So DC machines were used in the olden days where we did not have our power units technology. They vary the speed of the motor over a wide range. Now with the advancement of power units technology, we have vector control, which provides us with the same performance like our DC machine by using the induction machine itself. So compared to our DC machines, induction machines will be preferred, and when we go into the next few slides we will understand that induction machine and the permanent magnet synchronous machines are the ones which are widely used in our electric vehicle applications. Commutator-less, the second type of your electric motors. In this we have induction type, where the working principle will be based on the electromagnetic inductions. We will see that in the next slide. Synchronous machine, so it means it will be rotating at a particular speed depending on the supply frequency and the number of poles inside the machines. Brushless, permanent magnet brushless motors. Switched reluctance motor. Then inside the induction machine we have squirrel cage and wound rotor type, the two different types of induction machines. We will see which one will be used in our electric vehicles in the next slide. Wound rotor type, PM rotor, permanent magnet rotor based machine, and reluctance machine. So these are the subcategories of our synchronous machine. There we will be having wound rotor type or permanent magnet based or reluctance based, where we will not have any type of magnets inside the rotor. We will see the ones which will be popular for our electric vehicle applications that are highlighted over here. So the squirrel cage induction machine and PM rotor base or PMSM, so to say, and the SYN RM or synchronous reluctance machine and the switch reluctance machine. These are popular for our electric vehicle applications, including the PM brushless also. Now, let us see what are the options available with us. We have seen that. Let us compare each one of them with each other and see what are the advantages of each motor compared to the other one. So, first is our induction machine. So, what are the advantages of our induction machine? It has rugged design, excellent dynamic performance with proper control. So, as I said, in the olden days, the induction machine performance was not as good as our DC machines because we did not had our powertrains technology and advanced control techniques. But nowadays, the induction machine has given us the performance equivalent to the DC machine. So, almost we have eliminated DC machines from our applications and it has been overtaken by the induction machine. Easy availability and low price. So, the motor whichever is there, so it should be easily available and the price should be less, so that our electric vehicle manufacturing cost will be reducing. So, induction motor is a well established motor and the cost and it is easily available with us. So, that's the main advantage, as it is highly robust machine. So, the maintenance cost will also be less. So, the electric vehicle user will not be required for going into frequent maintenance if we are going for using the induction machine as the EV motor. Disadvantages of this one: low power factor, high rotor losses, because we will understand compared to our PMSM, this will be the two limiting challenges in the induction machine. But induction machines are cheaper compared to the PMSM. So, in low cost vehicles, they are used in the applications. Then PMSM, permanent magnet synchronous motors, they will be rotating at a particular speed, which we will see while discussing them in more details. So, here the main advantage of this one is, compared with the induction machine, the PMSM will be highly efficient. Why it is so? Because the rotor does not have any type of windings inside it. High torque or volume as compared to permanent magnet, has higher flux density, low rotor inertia, and as the rotor is not having any type of winding or its weight will be less, so it has low inertia. Good overloading capacity. So, PMSM, while discussing about the features required from our electric motors, we have seen this, it should have intermediate overloading capacity that is available with the PMSM. So, these are the advantages of PMSM. So, let us see the demerits of this one. Expensive due to the presence of permanent magnet, danger of demagnetizing of the magnet. So, as we are in India, in Indian country, we do not have any type of rare earth materials which are used inside the permanent magnet. When we go into this PMSM, we will see what are the materials which will be used to develop the permanent magnet, and we mostly depend on imports for manufacturing the PMSM magnets. And the other limitation of this permanent magnet is, over a longer run, it has the tendency of getting demagnetized and the performance of the motor may not be maintained with the lifetime of the vehicle. Then PM motor, brushless motor. So, what are the advantage of this one? High power density, compacted lightweight design because it is brushless design, low maintenance, high reliability and is long life because it has better performance in terms of mechanical terms because brushless operation is there. Low rotor losses, high torque density. The demerits of this motor, so high initial cost due to the permanent magnet. Again here, although we have eliminated the brushes in the motor, but still it has higher initial cost, requires sophisticated electronic controller and a risk of the same magnetizing of our permanent magnet, dependency on the rare earth materials. In India, we do not have any major source of rare earth materials, so we generally import those materials. So, these are the limitations of our PM brushless motor. Then switch reluctance motor, less costly compared to the PMSM and induction machine, this will be a better option. No magnets needed in this circuit. So, demerits wise, it is complicated in design, complicated control, speed control is vulnerable to temperatures. We will see the future electronic machine also in this lecture series. There we will understand that it will be simpler in construction compared to the induction machine and the PMSM, but it will have a requirement of complicated control technique and it will be highly sensitive to the temperature. So, from our previous discussions, let us form a comparison table of the 4 popular options which we have seen now. So, in this induction machine, PMSM, BLDC and DC machines are considered over here. Okay, so in the initial days where we wanted an low cost EV solution, DC machines were used. Nowadays, it has been almost limited to this PMSM and induction machine. 99% of the time we will be finding these two machines. Now, as an alternative to these machines, because we wanted to eliminate the PM or the permanent magnets in the motor so that our imports can be reduced. So, we are looking for alternate solutions like CNRM or SRM, where we will not require the permanent magnets. We will see this in details in the next lecture. So, efficiency wise, if you compare, so PMSM will be the best one. Torque density wise, PMSM is again the best. Cost wise, if you see, the induction machine is the best because it is less costly. The initial investment requirement is reduced when we go for induction machine because it does not require permanent magnets. The permanent magnets are the ones which increase the cost of our PMSM. Maintenance wise, these two machines are having the low maintenance. So, now from this comparison table, it is clear that where to select induction machine, where to select PMSM, where I want high performance and my initial cost can be beared by the customer, then I go for PMSM, and if I want a low cost solution, I go for induction machine. The other options, that is CNRM and our SRM, they are now under investigation, and there are few manufacturers which have started using them. So, maybe in near future the PMSM may be completely replaced by our synchronous reluctance machine, which we call as CNRM, or the SRM machine, switched reluctance machines. Then let us start with our induction machine. So, an induction machine, it works on the concept of rotating magnetic field. So, this rotating magnetic field we have discussed during our vector control of the inverter circuit. Okay. So, the same concept, it was first initially developed for the machines, then it was adapted for our control of the inverters. Okay. So, the concept of rotating magnetic field was introduced, or it was first used in our induction machine. Then we have used that for our DQ frame or decoupled control frame. So, those concepts are based on the same theory of our rotating magnetic field. Okay. So, what is the principle of operation of our induction machine? First is we should have a rotating magnetic field. We will see what are the conditions required to have a rotating magnetic field, and then when we have a rotating magnetic field inside the motor, and we on the rotor side we have two different architectures as already discussed, squirrel cage and our slip ring. During that, when there is an current carrying conductor inside an rotating magnetic field or varying magnetic field, it will get induced by an voltage or an electromagnetic force will be generated inside it, and an voltage will be there. If the circuit is closed, we will get an current, because the rotor circuit will be short circuited. In squirrel cage, it will always be short circuited. In slip ring, we will be short circuiting it through the external wires. So, the rotor head circuit is short circuited for both the types of machine, that is squirrel cage or our wound rotor type, and the current flows as we have an voltage induced because of the varying magnetic field. Now, we will have an current through the rotor winding. Now, when the current flows through the conductor, we know that it will be producing a magnetic field. So, the rotor current will produce the magnetic field. First is we had an rotating magnetic field which was produced by the stator, which had the supply or three-phase supply. We will see what is the requirement of rotating magnetic field to get produced. So, we have a rotating magnetic field from the stator side. Now, we have got another field. So, because of the interaction of these two magnetic fields, we generate a force which will be given by this equation. So, because of the production of this torque, because of the interaction of the two magnetic field, we get an torque inside the machine which will be responsible for its movement, or the rotor will start moving because of this torque which is generated. Okay. Then let us see the types of induction machines. So, how they are different. Stator side, the construction of both the machines, that is squirrel cage and the wound rotor type of induction machine, is the same. The change is on the rotor circuit. Okay. The first solution is squirrel cage type, where we will be having and conductors which will be placed in type of a squirrel cage. Okay, so this is from where this motor has got its name. So if you see, it is looking like a cage type of structure, and these rotor bars are there. So inside this rotor we will be placing rotor bars, and they are slightly tilted to improve the harmonic performance. They are called as skewed rotor bars to increase our harmonic performance, or the harmonic generation will be less when we go for skewed of the rotor bars compared to the case where we will be having the straight rotor bars. This will be having a better performance. Laminated sheets to reduce our current losses inside the circuit, and we will be having end rings which will be short circuiting the rotor circuit, so that the rotor bars whichever we have seen in the last slide, that they will be subjected to rotating magnetic field. So there will be an induced voltage, and we want the current to flow through it, so we have to provide a closed path. So we will be short circuiting the rods from both the sides of our rotor ends. So then the rotor shaft which will be connected to our differential and those mechanical components which will be responsible for moving the electric vehicle. Okay. So now the second option is wound rotor type. So as the name suggests, we will be having an rotor winding, okay, on the rotor also. So on the starter side we will be having a starter winding. In this case we will also have windings on the rotor side. So what is the advantage of this wood rotor type? So it provides a wide range of speed variation compared to the squirrel cage, because it can be doubly excited, that is we can provide an supply from the slip ring side. Okay. So DFIG or doubly fed induction machines, so when we give supply on the rotor side also, it is called a doubly fed induction machine. Those are suitable for our wind farms where we require very large range of speed variation, because the wind speed will be variable. Whereas for our electric vehicle applications, the squirrel cage is the one which is preferred over the wound rotor type, because the cost wise it will be less, and the speed range which is provided by the squirrel cage is sufficient for our electric vehicle applications. So we do not go for uncomplicated solution, because when I go for doubly fed induction machine, suppose by using the wound rotor type, the cost of our electric vehicle will be increasing, because it will require two converter sets, one for the feeding the supply to the starter and one on the rotor side. So squirrel cage is the one which is mostly used in our electric vehicle applications. Rotor bar are die casted, where bolted aluminum or copper rod is molded in the rotor slots. Okay. So the rotor bars will be made from aluminum or copper based on the cost, based on the performance required from the motor. The rotor bars are short circuited by using the end rings. Rotor material, so aluminum is the one candidate for that, and the copper is the other candidate. So here aluminum has only 56% of the conductivity of the copper. So conductivity wise copper is better, but cost wise copper will be more costlier compared to the aluminum. The material is, copper material is very costly. So copper rotor increases the power and torque density, but its cost will also be increasing. So the copper rotor reduces the overall losses of the machine. So these are the major advantages you will be getting if you go for copper based rotor, but the cost will be very high. So it can be used in high end vehicles, that is the vehicles used in our Tesla motors, Tesla cars are based on the copper rotors, because the cost is, initial cost is higher, and they do not have any limit on the cost, because they are concentrating more on the performance rather than the initial investment. But when we talk about our normal customers, they are more concentrating on the cost of the initial cost of the vehicle. So most of the time we do not use our copper based rotor, but we go for aluminum based or other alternative based rotor structures compared to the copper ones. Okay. The copper cost is very high. So the cost of manufacturing this copper based rotor is very high. So precise control axle is needed in this case. The copper rotor increases the motor mass, because copper is a dense material. So the weight of the motor will also be increasing. Solution, we will be using only the bars. So the bars which will be used inside the rotor will be made of copper, whereas the rotor core will be made of laminated silicon steel. Okay. So when we go for 100% copper rotor, so the obvious advantages are efficiency will be better, performance will be better, but the cost will be very high. So it is limited to the high-end electric vehicles, whereas for our normal or low-end electric vehicle or cost-effective solution of our electric vehicles, we will find this, that it will be rotor will be made of laminated silicon steel material, or steel will be used inside the rotor, and the bars which will be present, they will be made of coppers, such that our performance is comparatively good, but not as good as the 100% copper based motor, but we will be saving much amount on the cost or the initial investment requirement in this case. End rings, they are made of forged copper rings. Forging is a method to increase the mechanical strength of the material which is used over here. So the end rings will be having the, or the components which will be subjected to maximum stress. So we are trying to increase the strength of the material by going for forging of it. Okay. The laminated starter circuit, it is always fixed whether we go for induction machine based on the squirrel cage type or the wound rotor type, it will be the laminated silicon steel. But in our electric vehicle applications, we will be concentrating on the squirrel cage induction machine. There also we will find that it will be made from laminated silicon steel. Then rotor circuit is made of 3-phase windings similar to that of the starter circuit. The rotor windings are short circuited by using the end rings. If you go for the wound rotor type, so generally we will have 3-phase circuits, and we have seen that this wound rotor type is more suitable for wind applications because of high cost and need of maintenance, lack of steadiness. The wound rotor induction machine is less attractive than the squirrel cage for our electric vehicle applications. Okay, so wound rotor type, it is not that the machine is not at all good, so it is applicable or suitable for wind power applications where we require very high range of speed variation, whereas for our electric vehicle application it is not that much beneficial. So we generally use squirrel cage induction machine. So here also the rotor material will be laminated steel, and its windings will be made of copper wires. So in our squirrel cage we had copper rods, whereas in our wound rotor type we will have windings which will be made of copper wires. Here in this case, starter will be again made from laminated silicon steel, and the slip rings will be of bronze or brass because they are having mechanical performance, because the slip rings will be placed under the brushes, so it will be continuously moving with the rotor. So they will be subjected to high mechanical stress or friction will be there. So we go for this brass and bronze materials which have better electrical conductivity as well as mechanical strength. Then brushes will be made of carbon, and we place mica sheets below the slip rings so that the friction can be minimized. So the brushes will be of carbon because it is a good conductor of electricity, and this is how our wound machine will be constructed, and it is rarely used in our electric vehicle application. So we will be concentrating on squirrel cage throughout our discussion in this lecture series. Now let us understand how the rotating magnetic field is produced. So nowadays we have seen that we have stopped using our DC machines because induction machine and PMSM are well established technologies nowadays, or we have control techniques which give us better performance than the DC machines. So we go for AC machines. So now this AC machines, they work on the rotating magnetic field theory. Okay, so in this case, what are the conditions required to have a rotating magnetic field? First is we should have 3-phase distribution winding, and it should be supplied by 3-phase balance supply. So what is the meaning of that? What is the meaning of 3-phase distributed winding? So if I have the axis of A phase over here, the B phase winding and C phase winding should be space dispositioned by 120 degrees. That is, they should be having an 120-degree phase shift between them and the space. Okay, so we are talking about the mechanical position on the starter circuit. Okay, then it should be connected to balanced 3-phase supply. then these are the two mandatory conditions which are required to have rotating magnetic field. So, when we meet this condition, so over here if you see we have given a 3-phase balance supply and its instantaneous variation is shown over here. So, when I see the resultant of these 3 supplies which are given to the 3-phase distributed winding, so I will see that in space I will be having an effective rotating magnetic field which will be having an 1.5 times of magnitude. So, we have discussed this in more details when we were in the inverter circuits. There we have used this concept, but to and control an inverter in that case, in this case we are using that inside the electrical AC motors. Okay. So, the concept of this rotating magnetic field was first established in our electric motors, then it was adapted for DQ frame control of the inverter circuit. Now, the condition required for production of our rotating magnetic field. So, we have the 3-phase structure is the most popular one. We can have 5-phase, 7-phase or high number of phases. So, in that case also we can have rotating magnetic field production. So, what will be the requirement? That is, it should the space shift or in the actual mechanical plane, the winding should be placed by 360 by M. So, in our previous case we have discussed about 120 because it was in 3 phase 360 by 3. So, 120 degrees. So, the windings were placed in space 120 degree from each other, whereas if we have an M phase system, it should be placed by 360 by M degrees from each other. Then the rotating magnetic field, what will be the resulting rotating magnetic field which will be produced because of the M phase winding. So, it will be M by 2 into sin omega t. In our previous case, it was 3 by 2 into sin omega t. So, it was 1.5 times which is shown over here. Okay. So, when we have 3-phase supply, the resultant magnetic field which will be produced will be having a magnitude of 1.5 or a peak amplitude of 1.5, and similarly, we can have m number of phases and we will be getting the rotating magnetic field. The only exception is our 2-phase machines where we will be having 90-degree disposition, but the formula for our rotating magnetic field magnitude will be the same, that it will be m by 2. Okay. But here the 360 by m will not be followed for 2-phase, but it will be 90 degrees apart from each other. The windings will be having an 90-degree phase shift from each other. Okay. So, where this 2-phase system was used, it is the most popular example is our older ceiling fans or the fans which were used in the older case where we had an capacitor which was producing a 90-degree shift. Okay. So, there we were converting the single phase to 2-phase such that our single phase induction machine could be self started. Okay. So, now let us see the equivalent circuit of induction machine. So, this is the equivalent circuit of the induction machine. If you closely relate it, so it is having a similar structure that of our transformer. So, sometimes we see the induction machine to be a rotating transformer circuit because the equivalent circuits are similar. Okay. So, here we have various components which will be responsible for the losses inside the induction machine. So, what are those? This is R1 and JX1. They are the component which are present on the starter side. So, R1 represents the starter resistance, JX1 represents the starter leakage inductance. Similarly, the core will be having two components of losses, working component and the reactive component. So, this are responsible, or this parallel circuit is from the core material which is used, or because of the core substance which will be manufactured. So, we have seen what will be the material, silicon steel. So, based on this material we will be getting this core loss components. Then because of this presence of this loss components, our supply voltage which is at V, its magnitude will be reducing to E1. So, this will be the effective voltage which will be present in the space between the starter and the rotor circuit. So, E1 will be the reduced voltage inside the motor. Then because of the principle which we have discussed, because of the rotating magnetic field and presence of the short circuit on the rotor side or closed circuit on the rotor side, we will get an induced voltage on the rotor circuit which is represented ER. Then we will have the JXR or the equivalent reactance on the rotor circuit. Then this RR will be having two components. One will be the loss component and other one will be the useful component, which will be responsible for delivering power to our electric vehicle in our application as of now. So here why we have not considered the losses of the core material used in the rotor circuit, because of the two factors, that the power rating of the rotor will be much less compared to the power which will be handled by the starter side circuit. So when I say power, it means the frequency of induction. Okay, so here it brings us to the concept that is slip. Okay, the frequency of the starter will be 50 hertz for our conventional supply, whereas the rotor will be having a much lower frequency. So because of that, we are neglecting our core loss component on the rotor side of the circuit. Okay, so they will be negligible compared to the starter rotor loss. So that's why we are not considering them. Okay, so now this brings us to the concept of slip. Okay, so induction machine, it is not an synchronous motor, that is it will not be rotating at an synchronous speed, so which is given by 120 f by p, and this actual speed of the motor will be somewhat less than the synchronous speed. So the difference between the synchronous speed and the actual motor speed is qualified or defined in terms of slip. Okay, so slip will be your synchronous speed minus the motor speed by the synchronous speed, and this slip, as I said, synchronous speed will be 120 f by p, and motor will be rotating at speed which will be slightly less than the synchronous speed. So why it is so that the induction machine is not running at the synchronous speed? Because we are working on the induction principle, which requires the two magnetic fields should be present inside the machine. If the rotor is rotating at the synchronous speed, what will happen? There will be no relative motion between the rotating magnetic field. Rotating magnetic field will be rotating at the synchronous speed. Ns will be the speed of the rotating magnetic field. So if the rotor is also moving at the same speed, we will not have any relative motion between the rotor and the rotating magnetic field. So the second field will not be produced, so we will not have any type of voltage and there will be no current. So ultimately the torque will not be produced and your rotor will be falling back because of the losses which we have discussed now. So because of those factors, it will again fall back, and the other opposing will be our load torque. Okay, so that will also be there, and our torque production has become zero because of the load torque and the losses. It will fall back. So our motor runs at a slightly lower speed, such that the power which is to be delivered is generated because of the interaction between the two magnetic fields. Okay, so the slip will be increasing with the loading of the motor. No load slip will be much less, whereas full load slip will be slightly higher compared to the no load slip because of this factor, because more torque is required. So there should be more induced EMF, so the speed will be slightly decreasing. Okay, so we will stop at this point and we will discuss from this point in the next class.